Heterogeneous is describing phases of matter that are different throughout an equation, such as having a solid with aqueous and a liquid and another aqueous. This is a heterogeneous equation. Since pure solids and pure liquids do not have concentrations, pure solids and pure liquids would not exert a pressure, we do not include them in the equilibrium expression. For the reaction, solid A with aqueous B goes to liquid C and aqueous D. Only the aqueous adjectives have a molarity. So I include only the aqueous product over the aqueous reactant. I do not include pure solids or pure liquids in an equilibrium expression. Heterogeneous equilibria is showing solid carbon, but the amounts of carbon monoxide and carbon dioxide remain the same, and therefore the amount of carbon really does not have an effect on the position. I can have a big lump of carbon or a small lump of carbon, but I'm producing the same amount of product and reactant. So if I look at this equation, gaseous carbon monoxide is in equilibrium with gaseous carbon dioxide and solid carbon. Kc, the concentration of product over reactants. Concentrations are molarity units, so I use brackets. Notice the solid carbon is not written for. Kp would talk about partial pressures. Only gases have pressure. So partial pressure of CO2 set over the partial pressure of our reactant CO squared for that coefficient of 2. The solid carbon drops out. Practice writing equilibrium constant expressions and predicting the position of the equilibrium for the following. All right, aqueous nitrous acid with liquid water in equilibrium with hydronium ion aqueous and the nitrite polyatomic ion aqueous. The magnitude of the number is quite small, a number less than 1, so we know it's favoring reactant. Aqueous solutions have a molarity. Pure liquid water does not, and you'll see it drop out. Products over reactants. Pure liquid water, not written for. Water wouldn't have a molarity. It's the solvent. It doesn't have a concentration unit. Notice here in a double displacement reaction, calcium nitrate aqueous with sulfuric acid aqueous, forming a precipitate, calcium sulfate solid, and 2 nitric acid aqueous. The K constant's quite large. It's a number bigger than 1, so it's favoring the product side. Writing for everything aqueous, the pure solid drops out. The product squared set over the reactants, each raised to the first power. Calcium nitrate times the sulfuric acid, the concentrations of both reactants. The pure solid drops out of the equilibrium. When we calculate equilibrium constants from measured equilibrium values, the most direct way of finding it is to measure the amounts of reactants and products. That's sometimes very difficult to do. The reaction mixture may have different amounts of reactants and products, but the value of the equilibrium always remains the same. That's the term equilibrium constant. KEQ is indeed a constant. So if I remove some or make it back, we're going to shift the equilibrium to achieve the constant again. As long as the temperature is held constant, the equilibrium value indeed is also a constant. And it's quite independent of initial amounts, as the reactants will create products. So, in the beginning, thinking about, let's talk through what we're looking at. Initial and equilibrium concentrations, we have hydrogen reacting with iodine to form 2 units of HI. Notice here we have some initial values, and again measured at the equilibrium concentrations. Let's suppose we start this reaction with 0.5 moles of each reactant, but no product. Over time, equilibrium is reached. When we substitute in those values at equilibrium, never ever the initial amounts, but at equilibrium, the concentration of the products over reactants, squaring the product because of its coefficient of 2. 0.78 squared set over 0.11 times 0.11, we get a value of 50, an equilibrium constant. We run it again backwards. We don't have any reactant, but we have some product, 0.50. The reverse reaction takes over, and over time we reach an equilibrium concentration. But notice what's happened. Product over reactants, squaring the top because of the coefficient, we get the same number. Trial after trial after trial, the initial concentration has no bearing on the equilibrium values. That equilibrium will indeed be achieved as long as you kept the temperature the same. It's known as an equilibrium constant. That word constant, math friends, means it doesn't change. Calculating equilibrium concentrations, if we know the value of KEQ, we can also figure out the values of concentrations. So it's just stoichiometry. It can be used to determine the equilibrium concentrations of all the reactants and products if you know some initial amounts. Change is the concentration of material that you know to determine the change in other chemicals. I call these an ice chart. Let's talk through ICE, an ice chart. Let's see if we can't make sense in terms of a blank sheet of paper. Suppose we have the following. Oh boy, this is hard to read. 2a plus b makes 4c's. 2a plus b makes 4c's. So this is my way of doing double arrows. 2a plus b in equilibrium with 4c's. Alrighty. Suppose you have a reaction, 2a plus b makes 4c's. Aqueous, aqueous, aqueous. They're all adjectives of aqueous. With initial concentrations, and these are what's given to us here, initial concentrations of 1, 1, and 0 respectively. Oh boy.